This is lecture number 7 for Mechanical Metallurgy MAE 4333 class. We were supposed to do that a couple of weeks ago, but because of the test, we didn't do that. We have covered until lecture 6, which I went over again in the last class. So hopefully you have had a chance to go over and um, make sure that you understand the topic and the subject that is covered in that lecture. Okay, so what are we going to talk about in this class? We are going to talk about fracture. Why are we interested in fracture? We are interested in fracture because that is one of the prevailing mechanisms of failure of materials, and the fracture of materials is controlled by several factors. The most important one is the stress state that the material is in and any kind of flaws that the material might have in it. So, for example, if you are deforming a plastic type of a material or a polymer type of a material, so go back to uh, the differences between a thermoset and a thermoplastic material. So, what is the difference between a thermoplastic and a thermoset type of a material? Thermoplastics are, if you heat it up, it will melt and it will become plastic and very soft type of a material. But if you cool it down, it will become the polymer again. The second kind is a thermoset. So you are applying heat to set the material or set the crystalline structure of the material, the chemical structure of the material. So if you heat it up, the only thing that is going to happen is if you are beyond a certain temperature, it will just burn the material or it will just char the material. The other differences in plastics, the different kinds of plastics are whether it is a chain type of a crystalline structure or a network type of a structure. So if it is a chain, so if it is a serial chain, suppose you have say um, different kinds of links, a serial link. You can easily cut one link and break the whole material, whole chain, right? But if it is a network, it will be more difficult for you to break the chain. And the next kind is the difference between crystalline and amorphous type of a material. So if it is a crystalline type of a material, it is going to be much stronger, but it is going to be much more brittle. And if it is an amorphous material, it is going to be soft and easy to deform. So I hope you remember some of these concepts from uh, your ENSC 3313. So if you look at the properties of these materials, the degree of crystallinity and the density of the material as well as the strength of the material is well linked. So you look at this material, it's polyethylene. So if the density is 0.92 and it only has a crystallinity percentage of 65%, so most of the material, 35% of the material is amorphous. So you can see that it is much weaker and it only has a strength of 2 ksi. But if you go all the way to 96.5%, 0.965 density, so as close to 1 as possible, and it is 95% crystalline. So you can see that its strength is much higher. But what is it that you need to understand? This kind of a material, the last kind of a material is going to be extremely brittle but strong. Okay, so the different kinds of polymers are going to be like that. So there is going to be one homework that is going to be related to these plastics. So please take a look at that and try to solve that. So I mean, try to solve the questions um, asked in that homework set. Okay. So you can see that suppose you have what are called spherulites and lamellae. So if it is crystalline, you will find that some of these kinds of structures are going to be present. And if they are spherulites, they might be the starting point for failure. And lamellae might not do the same thing. So you can see that this kind of a structure is going to control the properties of your material. And the other uh, factor that matters is the cooling rate of your material. And you have a factor called free volume. So suppose you are cooling a polymer material, and if you cool it pretty fast, you are going to have, or between this region, you are going to have a glassy type of a structure. If if you cool it from this temperature to this temperature at a very slow rate, you are going to end up with an amorphous structure. But if you cool it very fast, like for example, you come to this temperature and it comes down all the way and then you cool it down, you are going to have a crystalline structure. Okay, so and beyond the glass transition temperature, it is going to be all crystalline. So, but what will also happen is that there is something called free volume of these materials, and the free volume is defined by the percentage of amorphous structure minus percentage of the crystalline structure divided by the volume of the amorphous structure, or this will be the density of the amorphous structure divided by the density of the sorry, yeah, density of the, it should actually say d subscript yeah, d subscript a divided by d subscript 0. I forgot what exactly it is. um, so these numbers will be given to you, or you can see that in the textbook or some handbooks in order to calculate these properties. Okay. You can also compare the mechanical behavior of these materials. So if it is an elastomer, it will typically have up to several hundred percentage strain that you can include in that. If it is a tough plastic that can withstand a lot of the impact without exactly breaking. I mean, it might deform, but it won't break. Okay, so it is going to be tougher than an elastomer. Elastomer can deform, but it is not as tough as the tough plastic. Why? I mean, how can you say that? Because toughness is going to be based on the area under the stress strain curve. Okay, so this tough plastic has got a larger area under the stress strain curve. And then if it is a brittle plastic, it fails with hardly any strain at all to failure. The other thing that you need to know is that many of these materials are going to be show the mechanical properties that are going to be dependent on its strain rate. So for example, if you pull it at a very slow rate, it may break at a much lower strength level. But if you pull it at a much faster rate, so 50% strain per minute or 5% strain per minute, that is quite considerable. Or you can actually say that so much the crosshead will move at a certain rate. So you pull it extremely fast, it will show that it is much stronger and it shows much higher strain percentage. So this is for polyvinyl chloride. It has been aged for 10 hours at 50 degrees centigrade. So some of the strain and things like that have been removed, and then you are pulling that at a certain rate, um, at a very fast rate. So higher the strain rate or higher the stressing rate, the higher the strength and higher the strain to failure, okay, for this material. So for many of these materials, I mean, even for metals and things like that, ceramics, the strain rate does matter. So faster the higher the strain rate, higher the strength. But it may not always be tougher than the other material. But in the case of plastics or in the case of polymers, the higher the strain rate, tougher the material. So properties of plastics are time dependent. So for example, if you are going to be looking at creep or creep relaxation, etc. So when ASTM discusses elastic modulus, the time aspect is also stated. Now, one thing to note is that the cooling rate does matter, and the temperature also matters. Okay, so when that happens, for these polymers, uh, and in this case, it is the time is plotted on a log scale. Okay, so when you are cooling it down, it starts beyond the glass transition temperature, it starts becoming leathery, and so this might be at room temperature. So when you start heating it up, it starts becoming leathery, and beyond a certain temperature, beyond the glass transition temperature, it becomes almost like a liquid. So this will be most important in the case of thermoplastics type of materials. Okay. So um, there is another factor called the shift factor for for reaching a specific elastic modulus. Okay, so that is equal to, so you will be given these. The room temperature values are not going to be valid at a higher temperature. Okay, um, for steels, the room temperature data are valid at even at 100 degrees centigrade, but for polymers they are not valid even at 40 degrees centigrade. Okay, so temperature and time connection matters for polymers. So you have families of plots such as these. They are often a necessary design input for polymers. And uh, isochronous, isometric, etc. are isochronous is at the same time. Isometric is for so if you are pulling these materials at a certain rate and things like that at say 40 megapascals per minute, it will it will show a certain behavior and certain amount of strain. So you can, so here again you can uh, so suppose you are pulling a material at 100 seconds, so it shows much higher strength. But if you pull it say up to 10 to the power 4 seconds, so 1000 seconds, you reach that at a rate of 1000, I mean you reach that strain after a certain amount of time. So that will change depending upon the strain rate. And even the onset of necking will be different for different kinds of applications. So the long and short of it is that polymers are going to be are dependent, the properties of polymers that you get are going to be dependent on the strain rate. Okay, it is not as significant in the case of metals or ceramics, but even in metals and ceramics you will find similar behavior, but in the case of polymers it is going to be much more significant. Okay, so just please understand that. So how do you analyze the, I mean, so many of the polymers are what are called viscoelastic. So they are neither viscous nor elastic. Okay, so they have partly, so the way they behave is going to be different. So the textbook has several pages on that. Please look through that and understand. So there is a exponential relationship with regarding time and temperature. Okay, so if you are going to keep it at a certain temperature for at a certain low certain stress level, it will start sagging and creeping. So it's there is something called relaxation time, and you can correlate the time and temperature with respect to that. So it's like a, so please take a look at the book and try to understand that, and we can go over that more. I will try to come back and go over this again later. So there are several other factors regarding polymers. So please take a look at all these things. So there are several figures related to all that. One thing to note is that many of these materials, uh, especially if it is a very crystalline type of a polymer, they undergo what is called crazing. Um, and they are both interesting and relevant. And there is local molecular motion that happens um, below the glass transition temperature. So at the very least, please look through the book and look at the figures. Okay. So when, especially in the case of polymers, uh, or even in the case of metals, there is reorientation of the crystalline structures during the necking process. Okay, so um, So if you have a single crystal that you are deforming, it forms like, under certain conditions it will form there is some tilting of the chains, some slipping and twisting in order to accommodate the strain that is being introduced into the material. Okay. I'm not going to ask you to draw this, but at least please understand that this is what is happening in this material in a larger scale at a molecular level. So if you have a brittle material, say for example if you have a very brittle plastic, or this could be a ceramic. Okay, so what are you going to see here? You will see that, what would you call this kind of a failure structure? This is a brittle fracture, what you would call a brittle fracture. It has not experienced much of a strain during the deformation process. How am I saying that? So if you look at the cross section from the side, I mean the section of this sample from the side, you will see that there is hardly any necking that has taken place. So if there is no necking, that means it is most of the time it is going to be a brittle material. And in this case, suppose for example, you can see that it has started from one end or in the middle. Most of the time that place where the failure has started from is a defect which is beyond the critical size for the material, and so the failure starts from that point and it releases that energy and fractures through the material in no time at all. So essential features of fracture are that they can either be ductile or brittle. If it allows plastic deformation, then it means the fracture is ductile. So if you look at the failure surface of a sample, say aluminum, where there has been some lot of necking that has taken place in the sample that broke. So what would you call the failure there if there is necking that has taken place? It is clearly a ductile failure. So, or even in the case of a thermoplastic material, if you are going to be pulling it apart, it elongates quite a bit. So if there is a lot of elongation, that means there is plastic deformation that has taken place. Okay, so that is a ductile failure. The other type of failure is a brittle failure. So in this case, only the elastic modulus and the stress are going to be related by the Hooke's law, right? So stress over strain is equal to elastic modulus, or elastic modulus divided by the so stress over strain is equal to elastic modulus. So elastic modulus times the strain is equal to stress. Now what is stress? Stress is the load divided by the area on which you are applying that load, right? So P, which you could call the load, divided by the area, which is A, cross sectional area, is equal to stress, which is also equal to E times epsilon. Okay, now If you recall from what we discussed in one of the earliest lectures, okay, we talked about what is theoretical strength and actual strength. So theoretical strength is approximately, is defined to be equal to elastic modulus divided by pi, and it is also defined as equal to under root E times gamma by A naught. So which is given by the figure number 71A. So please take a look at that. And so this is only in the case of a brittle failure. Okay, but suppose you have a ductile failure, then the strain and everything will come into play. So the definition of fracture is that it is the separation or fragmentation of a solid body into two or more parts. And for fracture or failure to happen, you have to initiate a crack, and that crack has to propagate through the material. There are two ways to deform or fracture as a material. You can either deform it in a plastic or a ductile manner, or it just fails like that with no strain at all, no plastic deformation at all. And in this case, brittle fracture means it propagates the crack extremely fast, almost at the speed of sound. And in that case, especially if you are designing a component, you should avoid that at all costs. So if you recall from your lab that you did for ENSE 3313, you recall that you tested a sample, a metallic sample like aluminum, that underwent lot of plastic deformation before it failed. And suppose you had a circular sample. If you put the two broken pieces together, it would have seen like it is a cup and a cone. So on one side it has a cup, and on the other side that is a cone. So you can put the whole thing together. Now it has deformed very plastically, so you cannot put it back into the same shape that you started out with. But still, you can see that the material has got a lot of deformation in it. Now, if you take a sample and it has got a notch in it, what does a notch do to the material? It introduces a stress concentration. So there is a local stress that is applied that is equal to approximately E over pi. And if you had a material that could undergo plastic deformation, then that stress concentration is relieved. So if you do not want a brittle failure, that material needs to have plastic deformation. You understand? Okay? Suppose you took freshly drawn glass fibers. I don't know if you have ever seen how glass fibers are drawn. So it's like a couple of stories, couple of building heights. Okay, so you pull melted glass from the top to the bottom, and then as you are pulling it, it creates a fiber that is like a maybe like a 5 to 10 microns in diameter. What is 5 to 10 microns? How much do you think is the diameter of your hair? Your hair is about 100 microns or about 0.1 millimeters. So a glass fiber or a carbon fiber is of the order of 5 to 10 microns. Carbon fibers are even smaller than that. It can be anywhere from 3 to 5 microns. Okay, so if you have that, and if you had no surface flaws or no flaws at all in that material, the glass fiber should have a strength of approximately 3 to 4 gigapascals or approximately 500 ksi. But what happens is that it does not, it breaks at a much lower strength than that because of the presence of flaws. Okay, so again, going over some of these relationships, E or the elastic modulus is equal to stress over strain, which is equal to sigma over epsilon divided by A naught. And so the critical stress that you need in order to break the material from a theoretical standpoint is equal to under root E times nu divided by A naught. A naught is the critical flaw size. Okay, so I know that some of these are probably not explained very well, so please take a look at the textbook. You should be able to find out what these individual parameters are so that you can understand this better. So one thing to note is that a material will fail depending upon the biggest flaw in the material. Okay, so suppose you have a flaw that is oriented right in the middle of this sample, and you are pulling this normally in the normal direction, that is exactly 90 degrees to the flaw that is present here. Okay, so what will happen? This part will easily open up and fail. So what you will find out is that this material or this block of material will fail at a stress level that is much lower than theoretically predicted, depending upon the number and the population of flaws in that material. If you take the case of a structural ceramic material, so like silicon carbide or titanium carbide or tungsten carbide, or even martensite for that matter. Okay, so if it has got flaws, they will fail according to a principle called viable statistics. Viable statistics is a statistical way of representing the flaw population that is present in a material. And how you get it is you take several samples, say 10 samples. Okay, you take those 10 samples, you break all of them, and you rank the failure stress of all those 10 samples from low to high or whatever. And then based on that failure value, you calculate what is called the probability of failure for this material to fail at that particular stress level. if you Google viable statistics, how do you get viable statistics for ceramics? You can understand that better. Okay, so you rank it and then you calculate the probability of failure at that value. So suppose you have a sample that broke at say 10 KSI and another sample that broke at 90 KSI. The average of your failure strength is going to be approximately, so it ranges all the way from 10 to 90. So depending upon the number of samples that broke, so you will get a certain value. Say for example, for argument's sake, let's say 50 KSI. And the standard deviation for your 10 samples is going to be plus or minus 20 KSI. So there is a lot of spread. Now, what is the probability that your sample will break at 10 KSI? It's going to be extremely small because maybe only one sample broke at that number. And 90 KSI also, you may have only one or two samples that broke at that value. But most of your samples would have broken at the average value. So you will have a higher probability for your sample to break at 50 KSI than at 90 KSI or at 10 KSI. And where is this statistics, where is this value going to be applicable? In design. So if you are going to be designing with a extremely brittle type of material, you have to take that into account when you are going to be designing components made out of these kinds of materials. So you have to take into account the fact that your component might fail at say 10 KSI or at 50 KSI or at 90 KSI. Okay, so you have to take that into account because it will help you to define the lifetime of your component. So how do you make sure that the range of your samples, range of failure values of your samples reduce? The way to do it is by minimizing the amount of flaws and minimizing the size of those flaws. How do you detect these samples? So you can detect them by different techniques like scanning electron microscopy or non-destructive evaluation and things like that. Okay, so if you have gone through design 1, MEC design 1 and gone through Shigley, you will appreciate that the concept of stress concentration was largely unknown before World War I. But after that, all these things started getting taken into account. So suppose you had a panel and you had a square hole in it. Those square hole had higher stress concentrations at the edges than in the center. But suppose you had a hole and it was a circular one or an elliptical one. Okay, so you can actually calculate the ratio between the stress at this edge versus the nominal stress that you are applying. So you can actually, it is approximately equal to, according to Shigley, this is how much it is going to be. So if it is a circle, A is equal to rho. Okay, so then the sigma local divided by the sigma nominal is going to be approximately equal to 1 plus root 2. So approximately 2.4, approximately 2.5 times. So your local stress is going to be 2.5 times that of the nominal stress. And if your local stress is going to exceed your failure strength of your material, it's going to fail. Now you can appreciate why we say that you have to design a component to approximately 2 times its 2.2 times its design stress. Okay. So the stress concentration here is approximately equal to, oh, okay, so this is equal to 3 approximately. Okay, so because this is just 1 plus 2. So the sigma local at this circular edge, edge of this circle is going to be 1/3 or 3 times that of the nominal stress that you are applying. So these the shape of these holes are going to control how much stress is applied at these edges and how that is going to affect your failure strength of your material or your component. So these are, so if you know the hole type and size and things like that, you can actually calculate what is going to be the maximum stress in this material. So if you know the applied stress normal to the major axis, if you know the size of your flaw A and B, you can calculate what is the value of rho, which is given by this equation B squared over A. So if you know the major and minor axis of your hole, you can actually calculate the radius of curvature. From that, you can actually calculate what is going to be the maximum stress that is being applied on this sample, or the stress that is at this edge here. Suppose the value of A is much less than the radius of curvature. Say for example, if it is a circle, then this gets down to 2 times applied stress into under root A over rho. Okay, so from that you can actually calculate these values. So I might give you some examples based on that, so you can actually calculate those values of stresses and things like that, or the stress concentrations. So the stress concentration factor sigma max is equal to approximately equal to 2 times sigma A into under root A over rho. And you are assuming here that, you are assuming that A is much less than, A is greater than rho, the radius of curvature. Right? I mean, this is what it shows, right? So on the arrow side, it is higher. So rho is much smaller than A. So based on this, you can also calculate the stress concentration factor. So the stress concentration factor is equal to 2 times, so this is the stress concentration factor, 2 times under root A over rho. So it is dependent on the crack length and the root radius. So if you understand these, you can also understand what you need to blunt the crack and what you need to do to get plastic deformation in your material. The other factor that I want you to understand is that um, there are different kinds of fracture modes that you can see. For example, they call it a flat and slant type of a fracture. Okay, so most of the time, if you have had a lot of plastic deformation, you will see that there is a lot of failure um marks that are present on the cross-sectional area where the fracture marks are present. But suppose there is no deformation, there is hardly any deformation at all, you will find that this area is kind of bright and shiny. If it is bright and shiny, that means that the failure is brittle. If it is dull and dark, that means it is a ductile failure. So for example, if your sample has undergone quite a bit of deformation, you will see what are called chevron markings. What are chevron markings? These kinds of uh, river marks or striations on this material are called chevron markings. So this is one side of your sample, this is another side of your sample. So it has kind of stripped apart from each other, from each side to cause this kind of to develop this kind of a fracture mode, macroscopic fracture markings. So if your sample has broken like this, so where is the crack nucleation site? Where do you think the crack has nucleated from? Most of the time, in this case, suppose you had a notch and the failure should start from this point onwards. So here, where do you think it started from? You can see that it started from probably the center and it kind of radiated out to all the points. Or it might have been from this point on, and it has radiated from this point on to all the rest of the areas of this sample. So the other nomenclature that I want you to understand is that there could be materials could or metals could fail in a transcrystalline or intercrystalline fracture. So what is transcrystalline? Transcrystalline means it goes between the grains, and intercrystalline means it is going between the grain boundaries. So when does intercrystalline take place? Intercrystalline takes place when your sample or when the grains are soft. And when do grains become soft? If you recall from our discussion on creep, when do grains become soft? When the temperature is above half the melting point in degrees absolute. So when that happens, the crack finds it easy to go between the grain boundaries. But suppose you are at a temperature much lower than that, what happens? And if you apply enough of a stress, it will go between the grains, in between the grains. Okay, so that is called a transcrystalline failure. Okay. So those are the two types of failures that you will typically find in metals. The other type of failure could be in a polymer or even in the case of a metal. Suppose there are a lot of voids in the material. Suppose you are applying you are having a sample that is undergoing creep. And during the creep process, it has created a lot of small voids. And those voids all coalesce together and become a huge void. And once that happens, it is no longer possible for the material to take the load. So it would rather fail. Okay? So if you have a metal and it has got a lot of these micro voids, they all join up together and then they fail, create a huge crack, and then it fails. Okay, so you can see that if you take the cross section and and look at it under the microscope, say the scanning electron microscope. The way in which these samples fail is also dependent on the effect of the state of stress. So for example, if you have these voids all elongated and you are applying a load exactly normal to that. So when that happens, it just pulls off and creates a failure point here. And if you take a look at it, so take a look at this surface from the bottom or from the top. You will see that there are a lot of these voids that have joined up together. But suppose you had these voids, they all were aligned in a direction that was different from the normal to the loading direction. Then you are applying extra stresses and extra stress concentrations at the edge of these holes. Then it will fail in a slightly different manner. And suppose these holes were all of the different sizes and shapes. That means the failure can take place in a different manner. So the long and short of it is that the fracture mechanism is going to be controlled by the state of stress in your material. So if it is a brittle material, you can clearly see that there is a small flat area in your sample that is close to the origination of the crack pattern. Okay, so that crack has come through here for a very short distance and then boom, it just radiated out like this. So you can see that the failure most likely started from near the flat fracture area. So please understand that. So if I give you a failure surface, and please go to the textbook and see what kinds of surfaces are present. Okay, so if you do that, you will find that near the fracture surface, near the fracture origination point, you will have a small flat area. And then it will go a certain distance in no time at all, and then it will say boom, 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 boom. It will just go forward and break the material together. Okay, so just wanted to tell you that. So intergranular fracture was what I told you. So the two kinds of failure in metals are transgranular and intergranular. So what is intergranular? Intergranular is a failure that is happening between the grains, intergrain. Okay, and when does that happen? So suppose you had two ice cubes and you put it into hot water. So the surface of those ice cubes start melting and becoming soft. Same way in a metal or in an alloy, when you have heated up the material to a certain temperature, the surface of those grains become extremely soft and now they are free to slide on top of each other. The other kind is failure that you will fracture in, that you will find in the case of polymers. So, for example, if you have a polycarbonate lens and you scratched it, is it easy to remove that scratch? No. Once it is introduced, it is introduced. You cannot do anything about it. Okay? So, if you have created that kind of a surface feature, it is called crazing, and that crazing will make the material, I mean, so for example, if it is polycarbonate, if you are using it for your lens, you can clearly see through that lens, right? Because it is clear and flat. But suppose you have crazed it and you had created scratch marks in it. Those could be happening right here. So you can see that here. And you cannot see through this glassy type of a material or a polymer type of a material. You can also create what are called dimple patterns in your samples in the case of polymers. So you create small dimples, they all join up and then bake in no time at all. So what are spherulites? Spherulites are areas where there are spherical particles, and that could be a weak point for the material when it is being tested in tension or in uh, uh, or 3-point bending. So when that happens, those could become areas where there is extra stress concentration. So when that happens, if there is extra stress concentration, then the material will tend to break or tend to fail at a much lower load than its original fracture strength. The other kind of failure that you will find is in the case of composites. So if you have composites, if you have fiber reinforced nylon or fiber reinforced carbon or fiber reinforced silicon carbide, a ceramic type of material, you will see that how is the fracture surface going to look like. Say for example, if there are fibers, they have all pulled out and they fail at a reasonably large strain to failure. Okay, so if there is pull out of the fibers, that means it has toughened the material, but it has also introduced quite a bit of fiber pull out. That fiber pull out essentially provides the samples uh, with areas where the fibers are missing. So if the fibers are missing in some areas, you know that it has been pulled out from the other side, and that contributes to extra strain to failure and extra stress to failure. If you had epoxy and you're adding microspheres, and those could be also create stress concentrations, and that will provide it with extra strength and toughness. So here are some example problems. So from that you can actually calculate the uh, sigma max. So you can see that E is equal to 95. So elastic modulus is equal to 95 gigapascals. but you can see that the maximum stress for this kind of a flaw size and the this is the surface energy of a small crack. You can see that the stress that you can apply is much lower than the elastic modulus or the theoretical strength of the material. So if you are given these equations, you should be able to calculate these parameters from in the test and homeworks. Okay. So one thing to note is that failure in materials is defined by a theory called Griffith's theory. So what does the Griffith theory say? There is a balance between, so suppose you have flaws and things like that, or you have a sharp crack. It has got a certain amount of elastic energy that is associated with that flaw. So suppose you are deforming a material and it has got all these cracks in it. So by creating these extra surfaces, you are going to be decreasing the elastic strain energy, which is at least equal to the energy required to create a new crack surface. I hope I am being understandable to you. So U equal to potential energy of the body with the crack, and U naught is the potential energy of the body without the crack. That is equal to, it's a negative parameter, minus pi sigma squared a squared t divided by E plus 4at gamma s. So this is, suppose you are creating a elliptical surface, you can actually calculate the change in potential energy associated with the introduction of a crack. So based on that, you can actually calculate the stress for under different conditions. Now, one thing to note is that if it is an extremely sharp crack versus a blunt crack, they are going to fail at different parameters. But it is not the whole picture. There are two types of stresses that are present in any given material. What are they? Those are called the plane stress and the plane strain type of a stress concentration. What does plane stress tell you? Plane stress tells you that the stresses are only in the sigma 1 and sigma 2 directions. There is no stress in the thickness direction at all. Whereas in the case of plane strain, you do not have strain in the third direction of your material. So I'm not going to go over the derivation of these parameters and things like that. What you need to understand is that for metals and polymers, the stress is approximately equal to under root 2E gamma S. Gamma is the surface energy of the particular crack or particular failed material. So based on that, you can actually calculate these things. And if there is plastic deformation taking place. That means this will change also. So these are the equations given for all that. So please take a look at the example problems, especially to solve the homework problems that I will be posting. So if you need a certain amount of energy to open up the crack, it will only happen if the energy is reaching a critical value G1C or GC. G critical, G is the shear modulus. Okay, so G critical, sorry, G is actually the strain energy release rate, not the, I'm sorry, I mean, we were talking about G is equal to shear modulus. It is not shear modulus here. Okay. So if you have a notch, you need to strengthen the material to prevent the failure from starting from that notch. So if you constrain the plasticity of the material, then the yield strength will go up to 2.5 times the yield strength you started out with. When that happens, you are going to be introducing more cracks into the material. But for that, you need a material that can undergo plastic deformation. There are only certain material that can do that. If it is ceramic or whatever, it will be totally different. Okay, so if you have a tough fracture, if you have a fracture that does not break the material, that means the notch was able to take a lot of plastic deformation, or was able to accommodate the plastic deformation. So these are some of the words and fracture features in plastics. So it is just a resource guide for you to study from if you want to do that. For ceramics, I mean, they behave in a slightly different manner. Okay, so you can clearly see where the fracture started from, and based on that you can calculate the mirror size and things like that, and that can be correlated uh, to the stress concentration and therefore the behavior of the material. For composites, you have figures from 738 to 740. The materials are a lot more complex, uh, and the matrix might fail before the sample, and or the interface might fail, or the test may be uh, test mode may differ, and it all depends upon the matrix and the fiber reinforcement. So I think I'm done with all this for this class. So let me stop here and I'll continue in the next class.